When we think about rolling motion, we actually need to think about this as combination motion, meaning that it is both translational motion and rotational motion. And I like this picture from the book, which has two lights on this wheel that is rolling to the side. One light in red is tracing out the motion of the rim. You can see that it looks almost like a circle. It's actually a slightly different shape, but you see that there's some sort of circular motion happening, while the center of the rim moves in a straight line. So the idea being that this is a sum of translation, where you would in fact have every single point on this disk moving to the side with the same velocity, and rotation, where now the velocity is actually different on different parts of the wheel. So let's go through this piece by piece. So translational motion, this is like what we've been doing in past chapters. We could treat our entire wheel as a particle because the entire thing moves together. Now to think about what's happening here, we're going to trace out three specific points: the center point, the top point, and the lower point. For rotation, we are then thinking about it rotating in place, not rolling, so just rotating around its center. So then, if we think about the velocity, we know that the velocity in this case is going to be given by the radius that it's at. So perhaps instead of capital R, let's use just lowercase r, times the angular speed. Now, if the object is rotating, the entire thing has the same angular speed. But the point at the center actually has a radius of 0. So in rotation, this has no velocity. The speed is 0. The top point's moving to the right at radius capital R, the radius of our wheel, times omega, and the bottom point would be moving to the left. So then, to think about the combinational motion, we just sum them. And we see that the point in the middle is then moving to the right at the same speed that it was moving just initially in the translation. The point at the top is moving faster because it has the sum of the rotation and the translation. And the point on the bottom actually has 0 speed because these two completely cancel. Why is that? We've used a specific assumption here, which is that there's a relationship between the center of mass motion and the overall motion. And another way of thinking about this is that this is just omega equals v over r. And this is the case where it's not slipping. So basically, once you've moved a certain distance in a certain time, that would actually be, if that's the circumference, 2 pi radius, so on. So the book goes through the derivation, but what's important is that if you have rolling without slipping, the bottom point is always stationary, and you get that from adding these two cases together. So this shows this a little more, that this is now summing together the different pictures. So again, we trace out one point, which is the same point on the wheel, and from that point being on the bottom to that point being on the bottom again, we would say that the wheel has turned one whole circumference, which is 2 pi r, and the amount of time that that has taken is in fact 1 period, capital T. So that's how we get to the relationship between omega and the speed of the center by using the fact that in this case, this is capital T, and when we have omega, that is just going to be 2 pi over T, where T is again period. And so in that case, when I say VCM equals 2 pi R over delta T, here I put in capital T, and I get at this point R times omega. So this was the result that I used on the previous slide. So again, this is the specific case of rolling without slipping. And in general in this class, we're going to be talking about two extremes. Either it's sliding such that it isn't rotating at all, or it's rotating without slipping. The in-between case is awfully strange to think about, and you would need more information. So that's what's going on here. Again, the center is always moving at a constant speed. If we trace out this point, the velocity it's moving at, the magnitude of the velocity is changing, but we can relate the overall rotation of our disk to the center by this equation. So now let's think about the kinetic energy of a rolling object. We've said that rolling is translation plus rotation summed together. Now the book went through a different derivation of this. I'm not going to worry about that. I'm going to make a slightly different argument. We can think about the energy the motion has from translation, and we can think about the energy of just the rotation. So the rolling motion is going to have one term that's coming from rotation and another term, and again we denote it cm because it's coming from the motion of the center of mass. And so you really have two terms in this kinetic energy, the rotational one and the translational one. And again, if you want to see, the book does a derivation just using this model and showing that it does simplify into these two terms. So these are both different types of kinetic energy, and again, this is really coming from thinking about every single point on here and the speed that it's moving at. So really there still is only one kinetic energy, but this is how to break it into two forms that are convenient to calculate.